All right, here we go. Today we're going to talk about how to deal with the force applied by a spring, and the equation for that is what's called Hooke's law. All right, so before we do anything, let me show you guys a quick simulation. Unfortunately, I can't do sort of live videos, otherwise I would show you a demo with some springs in my classroom that I can show you in class. So imagine holding a spring and stretching it, right? Or even like if you haven't ever played with a spring, a rubber band would work too, right? It's not exactly the same, but same idea. And so the idea is the more that you want to stretch that rubber band, or the more that you want to stretch that spring, the more force is required, right? So what we've got here is this little arm. This is analogous to your hand pulling on the spring, okay? And so, you know, if we try to stretch it a little bit, so I'm going to apply a force here of, you know, whatever, 40 newtons. Cool? So what that just did is I've applied a force. I'm holding it at rest, so that means the spring force is the same. Let's check this displacement. So that displacement is how far the spring has been stretched from its relaxed state. Okay? In other words, if I bring this force back down to 0, you can see that, you know, this line here, this line here is sort of the relaxed position. So that's x equals 0, right? Okay? So now, if I want to stretch it to the right, then I need my force to be, try again. If I want to stretch it to the right, then I want my force to the right, and you can notice that both the applied force and the spring force get bigger and bigger, right? They're equal and opposite because it's an action-reaction pair, right? The force of you pulling the spring is equal but opposite to the force of the spring pulling you, right? So that's Newton's third law. And you can see that as the applied force gets bigger and bigger, the displacement gets bigger, right? Okay. So this guy here, this little vector here is what's called x, and it's a measure of how much the spring gets stretched from its relaxed position. All right? And this works the other way too. Suppose we try to squish the spring instead of stretching it. All right, so there's my spring in its kind of relaxed state. That's as close as I can get it to 0. Oh, there we go. Cool. So now what I'm going to do is I'm going to squish the spring. So here we go. And you can see now the force of U is to the right and the force of the spring is to the left, right? Okay. This is probably as good a time as any to point out that notice at any given instant, the direction that the spring is pushing is opposite from the direction that the spring has been displaced, right? In other words, when you squish the spring to the right, the spring pushes to the left. Oh, sorry, I said that backwards. When you squish the spring to the left, the spring pushes to the right. So the direction of x and the direction of the force of the spring are always going to be opposite. Okay? So that's kind of the deal with springs. The more you squish or stretch it, the more force it will exert. The direction that you squish or stretch it is opposite from the direction of the spring, the force of the spring. Okay? So let's get all of this down into writing. Oops, wrong way. Here we go. Okay, so everything we're going to talk about is what's going to be for what we call an ideal or sometimes a simple spring, and it follows, as I said, what's called Hooke's law. All right? And Hooke's law says that the force of the spring is equal to this, so negative k, which is what's called the spring constant, times x, which we just talked about, how much the spring is stretched or squished from its relaxed state. Okay? The force, so in English what it's telling us is that the force exerted by the spring is directly proportional to the distance that the spring is stretched or smushed. Okay? So in this equation, Fs is the force exerted by the spring, and x is how much it's stretched or smushed. And then k is what's called the spring constant. All right? The spring constant measures kind of how stiff the spring is. The higher the spring constant is, the stiffer the spring is. Okay? And it's always going to be measured in units of newtons per meter. So suppose I've got a spring with a spring constant of, say, 4 newtons per meter. What that's telling me is that if I want to stretch that spring a distance of 1 meter, it's going to require a 4 Newton force. Okay? Now, maybe I've got another spring that's 10 newtons per meter. Oh, well, that's going to be stiffer because now it requires a force of 10 newtons to stretch it 1 meter, right? And the fact that it's newtons per meter, that tells us that with this green one here that I'm circling right now, if the spring constant is 10 newtons per meter, that means it would take 20 newtons to stretch it 2 meters, or 30 newtons to stretch it 3 meters. Okay? So that gets back to this idea of the force being proportional to your x value, how much you've stretched or squished it. Okay? The negative sign in the equation just shows us that the direction that you stretch it, so if I stretch or squish my string to the right, then the spring is going to push to the left. So that's what this negative sign is in here for. Okay? So why don't we do a quick example? All right? So a really common way to stretch a spring is just by simply hanging a mass from it. All right? So here we've got exactly that scenario. All right, and so what I've got is, I'm just going to use the spring here on the left, okay? And so you can see there's this dotted line that represents x equals 0, okay? And let's see, I'm going to tweak this. Oh yeah, did I already do it? I think I did. Yeah, okay. All right, so what I'm going to do is I'm going to hang a spring, or hang a mass from this thing. So before we do any kind of math on it, let's just, so if I hang 50 grams from this, then you can see that stretches at 10 centimeters, okay? And if I hang 100 grams from it, it should stretch twice as far, right? Because it's going to need twice as much force to support it. And so you can see that stretches at 20 centimeters, all right? And if I go all the way up to 250 grams, it's going to stretch way further, stretches it to 50 centimeters, okay? So the more mass you hang from the spring, the farther it stretches. Hopefully that's somewhat intuitive, all right? Now let's do some simple calculations for it, all right? So let's go back and hang this 50-gram thing from it, all right? So when I do that, it stretches, whoa, try again. So when I do that, it stretches 10 centimeters, right? So, all right, so here we go. So over here, what we've discovered is that if the mass is 50 grams, oh, well, that's the same as 0.05 kilograms, then let's think about what's going on. So here's my mass, 0.05 kilograms. Okay, well, that means the force of gravity is pulling down with 0.05 times 9.8 gives us negative 0.49 newtons, all right? And then the fact that it's hanging at rest tells me my net force is 0, right? Oh, well, that means that my upwards force from the spring has to then be positive 0.49 newtons. So as long as your object is in what we call equilibrium, as long as it's not moving, then your acceleration is 0, your net force is 0, and so your force of your spring equals your force of gravity. All right? So here what we've got then is our force of our spring is positive 0.49 newtons, and the simulation is showing us that the x value is negative 0.10 meters. Negative because it stretched downwards, right? So remember, Hooke's law says the force of the spring equals negative k times x. So let's plug in our numbers. So the force of the spring is 0.49 newtons. That's equal to negative some value k that we don't know, times x, which is negative 0.10 meters. Two negatives here make a positive. Divide by 0.1, and we discover that k is 4.9 newtons per meter. So that's the spring constant for this spring. All right, so let's go over here and let's make a note of that. So our spring constant is 4.9 newtons per meter. All right? So for every 1 meter I want to stretch the spring, I need 4.9 newtons of force. Quick side note while I'm thinking of it, notice when I write my spring constant k, I'm going to use a cursive letter k. It's meant to be a lowercase letter k, but when we get to AP, there's also going to be another thing that's a capital letter k. These are a little bit tough to distinguish sometimes. So I always write my lowercase letter k's in cursive, all right? If you're thinking about maybe taking AP next year, I recommend that you write your spring constant K as a lowercase k, all right? Or as a cursive K, sorry. All right, cool. So that's that. All right, so now that we know what our spring constant is, we should be able to make some predictions. So let's replace this 50-gram mass with the 250-gram mass, and let's see if we can figure out what's going to happen then. All right? All right, so suppose that I do that. So suppose the mass is 250 grams. Remember, that's the same as 0.25 kilograms. Well, then once it reaches equilibrium, you know, we're going to have two forces. The force of gravity would be, well, if you do 0.25 times 9.8, it gives you negative 2.45 newtons. Oh, well, that means the force of the spring would have to be positive 2.45 newtons. So we ought to be able to figure out how far it stretches, right? So let's see, the force of the spring needs to be positive 2.45 newtons to support this dude. That's equal to negative 4.9 newtons per meter times x. Divide both sides by negative 4.9, and your x turns out to be negative 0.5 meters. All right, so let's try it and see if it works. Let's hang this guy from it. Notice if I just let it go, it bounces around a little bit. But once it stops bouncing, oh, there it is. It's stretched. Whoa, I did it again. It's stretched to, oh, goodness. I just said goodness. All right, so it stretches half a meter, right? And notice the negative sign tells us that it's stretched downward. Okay? The other thing worth noting is that the first mass I used was 50 grams. And 250 grams is 5 times as big. And notice the spring stretched 5 times as far. Okay? So that's how you use Hooke's law. All right, so hypothetically, suppose I pulled the spring down a little bit extra. Let's kind of clear this off here. All right, so right here, our net force is 0, right? All right, but suppose I pull it down. Suppose I take the mass and I grab it and I pull it down to 70 centimeters. Okay, well at that point our x is 0.7 meters, which means the force of the spring is negative k times x. So basically what I'm doing is I'm going to go, I'm going to pull this guy down to here and then let it go. Okay, so I don't want to do it yet, but so let's go back and do our calculations. So let's see, so the force of the spring is, oops. So the force of the spring is negative k times x, which is negative 0.7, right? So this gives you 3.43 newtons. So what's happening when it's here is this. Our force of gravity is still 2.45 newtons. Now my force of the spring is bigger, right? Because I've stretched it down farther, resulting in more force. Okay? And so if you go through and figure out your net force turns out to be 0.98 newtons upwards, and so you get an acceleration upwards of, if you do the math, it turns out to be 3.92 meters per second squared, right? Just using acceleration is net force over mass. Okay? And the idea is we've got more upwards force that produces an upwards net force and an upwards acceleration. Okay? So let's try that. Oh yeah. So when it gets to this point right here, it's accelerating upwards, right? Oh, and notice it stops up here, right? Stops at both 70 and 30 centimeters. So the idea is when it gets to this red mark, now what's happening is our force of gravity is still 2.45 newtons. But what happens is at this point, now it's stretched less, so now the force of the spring is actually less than gravity. It turns out if you do the math, it's 1.47 newtons. So now we have a downwards net force and a downwards acceleration, which is why it stops at this point and comes back down, right? Because you've got more downward force to stop that upward motion. Okay? So that's the deal there. I don't know if that helps any. Here you can see the force is changing. You can notice that the size of the red force, gravity, stays the same, but the size of the blue force is always changing. Here's your net force in black. Okay? So there you go. All right. So that is how you use Hooke's law. Now, sometimes we have more than one spring. Okay? So what happens then? So, holy moly, look at this mess. All right. So we already talked about what happens if you've got sort of one spring, right? So let's do this. Let's pull with 100 newtons on this thing. All right. And so notice, in this instance, with one spring, so notice all of the numbers are going to be the same here. So in this instance, my spring constant is 200 newtons per meter. I'm applying 100 newtons of force, and that resulted in my x being 0.50 meters. Okay? Sometimes, though, we have more than one spring. Okay? Let's see. I'm just noticing. Do you want to do that? Oh, I see. No, we don't want to do that. Okay. All right, so there we go. So there's one spring. Spring constant is 200 newtons. An applied force of 100 newtons makes it stretch half a meter. Now, what if we have a scenario like this? Oh, now I've got two springs. Notice both springs, again, have a spring constant of 200 newtons. But what's happening is they're both sort of attached to the, sort of my object, right? So let's go ahead and apply a force of 100 newtons again. Oops, try again. Let's apply a force of 100 newtons. And you can see, oh, it only stretched half as far, right? So it's like these two springs worked together to result in sort of a bigger overall spring constant, okay? It's like this spring constant is much tougher than this spring constant, right? Because you're stretching two springs instead of one, okay? So these guys here, and I'll give you a definition for this in a minute, it is in the notes, but so these two springs are connected in what we call parallel. All right, they're called parallel because each of the two springs independently are attached to the object that we're trying to move, okay? Now, sometimes the springs are connected in what's called series. All right, so notice here, I don't know what I'm going to do. Well, I'll write it all out in a minute. So anyway, so notice here, our spring constant got bigger, which meant the distance it stretched got smaller. Okay, so this is a bigger K and a smaller X. Okay, for the same amount of spring force, right? Now, sometimes, instead of having the springs side by side, the springs are attached, end to end. Okay? So here what happens is the springs kind of share the load. You can kind of think of this as being a longer spring, and so that makes it easier to stretch. And so what happens is that same applied force of 100 newtons, holy cow, look how far that stretched it. Okay, so here, these are connected in what we'd call series, and it results in a smaller K value and a bigger X. Okay? Again, it's analogous to making a longer spring, so you've kind of got more coils, which makes them easier to pull apart. Okay? So let's put this all in writing, and there are two quick equations we got to learn. All right, so let's get out of here. Let's go over here, here. I don't know that we need to do this example. I think we kind of covered that. All right, so here we go. So here are two different possibilities. So in blue, over here, you can see springs in series. So you've got the two springs, and they're connected end to end, right? And it results in a smaller equivalent spring constant, sometimes called a total spring constant. All right, and so here's the equation. So if you want to find so suppose we wanted to treat this as like one big spring, okay? Then that one spring would have to have an equivalent spring constant that satisfies this equation. So 1 over that equivalent spring constant is 1 over spring constant number 1 plus 1 over spring constant number 2. All right, so the idea is usually you'd know K1 and K2, and then you would do algebra and solve for a K equivalent. All right, so we'll do an example of this in a minute. Let's do parallel first, though, because it's a little bit easier. All right, so for parallel, the idea is now both of the two springs independently are attached to my box, right? Okay, so this little bar here is just kind of like allowing the two springs both to attach to the box. Okay, so when springs are in parallel, all of the springs are independently attached to the object. And what it does is it results in a larger equivalent spring constant. And here the equation is much easier. You just add your two spring constants. All right, so let's do an example of each of those. Okay, so this first one says with two springs with spring constant of 30 newtons per meter are both independently attached to the ceiling. So let's draw that. Here's our spring. Here's our spring. Mr. Hacker hangs a banana from it. So here's our banana. All right, so this guy, spring constant number 2 is 30 newtons per meter. This guy, spring constant number 1 is also 30 newtons per meter. The banana has a mass of 0.4 kilograms, so let's go ahead and draw in our forces. So the force of gravity here is going to be negative 3.92 newtons. That means my combined force of my springs also has to be 3.92 newtons. So force of springs is 3.92 newtons. To be clear, that's the combined force of the springs. We're trying to figure out how much the two springs stretched. So what we have to do is we have to find our equivalent spring constant. All right, now, because these are connected side by side, these guys are in parallel. All right, and so the equivalent spring constant when they're connected in parallel is just K1 plus K2, which for us is just 30 plus 30, or 60 newtons per meter. Okay, and then I know the force of the spring is 3.92 newtons. So now all I'm going to do is go, well, force of the spring equals negative K times X. 3.92 newtons equals negative 60 newtons per meter times X. Divide both sides by negative 60, and your X turns out to be negative 0.065 meters. So that's how far the springs stretch down, about 6.5 centimeters. Okay? So keep in mind that that X value is in addition to the unstretched length of the two springs. Okay? All right, so that's how you do it when the springs are connected side by side in parallel. When they're connected end to end, the math is a little bit trickier. Notice, I guess I should point out here that this wouldn't have been any harder if these two spring constants had been different, would it? Right? You know, if it had been 30 and 20, then this would have just been 50, right? Also worth noting is that this 60, this equivalent spring constant, is bigger than either of the two individual ones. All right? So there we go. So that's parallel. Now, when they're connected in series, it's slightly different. So here what we've got is a spring with a spring constant of 20 newtons per meter is attached to the ceiling. And then a second spring with a spring constant of 30 newtons per meter is attached to that. And then we're going to hang a banana from it. And the mass of the banana this time is 0.6 kilograms. These are pretty big bananas. So let's go ahead and put in our forces. So let's see. So if it's just hanging there from rest, oh, it really changed the color. Oh, I see. There we go. All right, so here we go. So our force of gravity here turns out to be 5.88 newtons, negative. If it's hanging at rest, then my combined spring force is also going to be 5.88 newtons. But we need to find our equivalent spring constant. So here's that wacky equation. I just said wacky. So here we go. 1 over equivalent K is 1 over K1 plus 1 over K2. Notice these guys are connected in series this time because they are end to end. So we're going to get 1 over equivalent spring constant. Oh, quick side note. I think when I wrote up my answers for the homework, I think I used KT, like total spring constant, instead of K equivalent. So if you see KT anywhere in any of my PDFs and stuff, that's the same as K equivalent. All right, so this is 1 over 20 plus 1 over 30. So depending on your fraction skills, there's a number of ways of doing this. I usually just use my calculator. And so I literally just type in 1 over 20 plus 1 over 30. I'll write it out in steps. So 1 over 20 is 0.05. 1 over 30 is 0.03 repeating. So this gives you 0.083 repeating, which means that K equivalent is 1 over that. You're basically taking the reciprocal of both sides, and it gives you 12 newtons per meter. All right? So the idea is these two springs here can be replaced with one equivalent spring whose spring constant is 12 newtons per meter. Notice it's a smaller spring constant than either the 12 or the 30. Okay? So now our last step then is to do the math. Oops. So force of the spring is negative K times X. So the force of the spring has to be 5.88 newtons per meter. That's equal to negative K, we just decided was 12 newtons per meter, times X. Divide both sides by 12, and you end up getting negative 0.49 meters. So that's how far that one stretches. All right? So there you go, Hooke's law. 3 equations. Hooke's law, and then these two guys. I should note, these 2 equations are not on your equation sheet because they're new this year. So I guess until I say otherwise, you got to memorize those. Or hopefully I'll find time and laminate some new sheets. Okay, cool. I'm going to shut up. Have a good day.